I'm super excited because I learned how to combine two videos just now. So in case I need to stop this video in the middle of it, because I think 2.5 is going to be pretty long. So thinking about like 40 minutes-ish. So far on Canvas, you guys have access to 3 videos. So by the time I'm done with it, we will be done for the lesson today. But instead of uploading a 3-hour-long video, I did divide it up to, let me see if I can just enter a student view. Just to see what you guys are seeing. Unknown error. Ugh. Okay, so if I go to modules and look for our day, November 11th. Okay, right here. November 11th, I see that the blank notes are available. I see there are 3 videos uploaded so far, 37 minute, 36 minute, 26 minute. Hopefully this is the last one if I can finish 2.5 in a single video, but I'm gonna go ahead and probably stop around 40 minute-ish because I don't want to make it longer than, you know, like an hour long, right? So, and I also been posting the notes that I took in each of those videos. So this was the note from the first video. This is the note from the second video and third. I didn't combine those two, but first part, example 1 through 4, that took me about 36 minutes to go over. And page 3 and 4, that was a little bit shorter, about 30 minutes. So the notes are over here if you just wanna, well, if you're listening to this, then you are watching the video. So thank you. Let me go ahead and finish 2.5. And when you are done watching and taking notes, and you may do the My Math Lab homework first, but I also have a couple problems that I want you to try. So number 1 is about dose of a drug. It's an exponential decay. So after our lesson on 2.5, you should be able to do this. And exponential decay and a doubling time. Asking for the growth rate, given the doubling. So number 3 is similar to what we did in section 2.4. So you are always, I want you to email me if you have any questions on the daily problems, because I can go over those for you too. But I also wanted you to try them first, because you learn by you trying something yourself. And if it's wrong, I can grade it and give you feedback. But anyways, that's enough of talking. Let me go back and teach you 2.5. So here's 2.5. In this section, we're looking at application questions that's involving exponential decay. So this is section 2.4. We looked at investment, how our money grew, or how a painting's value went to like $1 billion. So we were looking at a whole bunch of functions, examples of like a growing function, like the value was increasing. But now in this section, we're going to look at functions that are decreasing. Nothing much difference. I want you to take a look. For exponential growth, we used this ending value p equals p naught, initial value times e raised to the kt power. Okay, now look at the exponential decay function. Almost the same thing, right? P equals the ending balance or ending amount equals p naught, the initial value times e raised to the negative kt. Okay, so if that rate is negative, then we're going to have a decay. Okay? Alrighty, let's take a look. So physical science, decay. So we have strontium 90 has a continuous growth. I'm sorry, not a growth anymore. I should be careful. We're looking at a continuous decay rate of 2.8% per year. I want to go ahead and write this down as 0.028. So if we are writing this equation, guys, strontium is going to have, let me use P. P for the ending balance, ending amount. However much we started with times e raised to the negative 0.028 t. That will be the equation using our continuous compounding function. The rate of change of an amount and of this radioactive isotope is given by, now this is similar to what we saw on the on page 3 and 4 of our section 2.4 notes, right? So this is a way for us to write the derivative or the rate of change function of an exponential function with base e. What we can say is that the rate of change derivative is going to be equal to that rate, that decay rate, times the function value at that time. So both of these are good. Well, because I'm sure they're going to ask us to write the actual function using what they gave us. So let's read part A. Find the function that satisfies the equation. Let n naught represent the amount present at time 0. Okay. So here let's go ahead and write the function. So n of t, okay, is equal to n naught. Okay, I'm reading it as n naught. N sub 0 is also a way for you to read it, but n naught is how I read it. N naught times e raised to the r times t power, right? Where r is the exponential decay. It's decay, so go ahead and write down 0.028, but to make sure that is a negative, times t. So we wrote it. So if someone asks you to find the derivative of it, then you're going to just have that n naught times e to the negative 0.028t. But using the chain rule, I know that you will multiply that by the derivative of negative 0.028t, right? And what I'm doing right now, I already found the answer. I already wrote the answer for part A, but I'm checking it. N naught times e to the negative 0.028t times the derivative of this linear function is negative 0.028. Okay? So what do we have here? N prime, which is, oh gosh, you guys, I really need to add more room to these problems. N dn dt, derivative of n with respect to t is equal to, now what is this? What is this? This is the original function n, isn't it? That's n times this constant, negative 0.028. And this is matching what they gave us in the beginning. So the next couple steps that I did, this much work was just to check. Okay, but this is my answer. This is the answer to part A. Okay, alrighty, let's keep going. We're gonna use either that function that we just wrote or the given function to answer some questions. Suppose 1,000 grams, so they are saying n naught is equal to 1,000. Of strontium 90 is present at t equals 0. How much will remain after 70 years? So if you want to find how much of this strontium 90 we're going to have, we're going to use that n of t function, which is, now by the way, n naught is what? 1,000 here, times e to the negative 0.028t. So let us find n of 70 years later. 1,000 times e to the negative 0.028 times 70. I'm sure we're going to get to half-life later, but this radioactive, is it radioactive? Yes, it is. So it's decreasing. I watch a lot of TV shows during spring break, and one of the things that I watched was Chernobyl. Is that how I'm saying it? Oh, wow. It was about nuclear plant exploding. Oh, wow, what a great series. But anyways, all right, so this is how what I got. When I typed that in, I got 140.86 grams remaining or present at remain after 70 years. So we started with 1,000 grams. So in 70 years, we still got a little bit, but it's not as much. The amount decreased. All right, let's do one more. They said find the rate of change of the amount of strontium 90 after 70 years. Okay, so there are two ways to do this. You can find the derivative function, which we did, and then plug in 70, or we could use this given this red equations. What they gave us was n dn dt is equal to negative 0.028 times n. What does that mean? That means derivative at 70 is going to be equal to negative 0.028 times the function value, how much is left at 70 years, after 70 years. So I'm going to go ahead and multiply this by the answer that we found, 140.86 grams. Okay, grabbing my calculator, negative 0.028 times 140.86. That comes out to be negative 3.94. There more, but I'm just going to round it however I like. Negative 3.94 grams per year. So you see this is a negative, right? So after 70 years, it is going down about 4 grams per year. Okay. Alrighty. Let's take a look at the last one. How long will exactly half of the original 1000 gram remains? So what we know is this. We started with n not equals 1000. We want the ending value to be half, 500. And everything else is the same. So let me write down the original function. N of t is equal to 1000 times e raised to the negative 0.028t. But this time we're going to plug in that n of t is 500. And guess what we're going to solve for? We're going to solve for time. How long will it take for this to become half? All right, so first divide both sides by 1000. 500 divided by 1000 is half. E raised to the negative 0.028t. By now, you guys are like pro at solving an exponential equation. So you know the next step is to take natural log of both sides. Natural log of 1/2 is equal to natural log of e to the negative 0.028t. Okay, losing the log property. Let's bring this guy down. So I'm going to get natural log of 1/2 is equal to negative 0.028t times natural log of e. And what is that? That's just 1. So we got natural log of 1/2 is equal to negative 0.028t. So final step, guys. Final step is to divide both sides by that negative decimal. So t, how many years will it take for the strontium to become half of what it used to be? Natural log of 1/2, I'm typing that in, divided by negative 0.028. And that came out to be 24.76, and I'll just round it to the nearest hundredth. So it's going to take about 24.76 years, and that is the strontium 90's half-life. Okay, that's how you can find it. Now, let me give you a little half-life formula. Half-life. If they ever ask you for a half-life, what you can do is this. You can do natural log of half divided by the decay rate. Okay? Or I should just say k. I should say, well, negative k. Okay? So wait, hold on a second. I think I got a, oh yeah, theorem 10. The page right next to it. Let me erase this because we got it all right down here. So theorem 10, and there's a nice box organizing a formula for decay rate k and half-life. So if they're asking for half-life, this is going to be the half-life. Okay, this is the half-life. You can do this, ln divided by k, or t equals ln of half divided by negative k. Both are going to give you the half-life. Okay. K is the decay rate, but they're just solved for each other, decay rate. So maybe instead of solving the equation like we did on example 1D, we can just use this formula down here. Let's try that. The decay rate K for a particular radioactive element is 3.2%, 0.032. Let me write that down. Where time is measured in years, find the half-life of the element. All right, here's the half-life. This is the half-life formula. And I encourage you to use it. Now you know this. So half-life formula is ln2 divided by k. Natural log of 2 divided by the rate of 0.032. Get your calculator, type this in. ln natural log of 2 divided by 0.032 comes out to be 21.66 years. Now the equation that I came up with on the previous page is slightly different, but it should give us the same thing. So let me try the other way. T equals natural log of 1/2 divided by negative k, negative 0.032. If you do that, natural log of 1/2 divided by negative 0.032, it gave us still the same exact answer, 21.66 years. So up to you, the red equation or the purple equation, you now know a formula for half-life. So we got the answer. Yay. See, after 2.4, 2.5, they're just similar. So I don't know if I'm going, I think I'm going a little bit faster than the speed I was going at, going over 2.4. So hopefully this is okay. All right, physical science, another half-life problem. Plutonium-239. Oh, plutonium. What movie did I just watch the other day? They were selling, Tom Cruise was buying these plutonium, like nuclear. Okay, anyways. Common product of a functioning nuclear reactor. Oh, can be deadly for people exposed to it. I wonder if that's what they have in Japan right now. Fukushima? If decay rate is about, oh my gosh, look at that tiny decay rate. It's not going down fast enough. It's not decaying fast enough. If this is so deadly to people, we want it to go away faster. But all right, if I divide this by 100, I will get 0.0000028. That's a tiny decay rate. So this is not going to go away for a long time. All right, what is that half-life? Okay, let's find that for them. Half-life is ln2 divided by k, or r, sorry. I keep using r. R is my variable for rate. Whenever I see rate, I will use r. But it looks like our textbook started to use k recently. All right, let's divide it by 0.0000028. So how long will it take for an amount of plutonium-239 to become half of what it used to be? How many years will it take? Let me type this into my calculator. 0.0000028. Oh my goodness. This is not good. 24,755 years. Oh my gosh. This is, when I get it, I don't know if you guys do this, but some people, like, they type in, oh, my final answer is negative 47 watermelons in a word problem, and they don't really go back and question themselves. Like, this doesn't make any sense. You know what I'm doing on my laptop is I am Google searching plutonium-239 half-life, because that's a long year. And they did say, guys, it does say the plutonium-239's half-life is 24,100 years. Maybe our textbook, or maybe this is an example that I come up with. I may have just changed the number a little bit, but yeah, that's so long. Okay, how dangerous is plutonium-239? I should go read this on my own time instead of using my teaching time, so I will go ahead and go look at another example. But this is fascinating in a bad way, because it's deadly to people when they are exposed to it. All right, let's keep going. Carbon dating. The radioactive element carbon-14, that's a popular element, has a half-life of 5,730 years. So it's gonna take carbon-14 this many years to become half of what it used to be. The percentage of carbon-14 present in the remains of plants and animals is used to determine age. Oh, so that we can figure out how old this dinosaur fossil is. Archaeologists found that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14. How old was the linen wrapping? Okay, so I think I'm going to go ahead and find the rate here. We're going to find the rate. All right, so I can use this rate formula. Let me go ahead and copy this rate formula. copy this guy down here. Okay, so what is the rate? We do know that the half-life is 5730 years. So the rate, exponential decay rate, K, is equal to natural log of 2 divided by 5730. Let me put this into my calculator, guys. I'm popular today. I'm getting all these emails. All right, 5730. It comes out to be, oh dear, it's tiny. 0.000120968. I can multiply this by 100, but that's still a very tiny number. So this is the exponential growth, decay rate. Because it was so small, I try to be as accurate as possible by writing down all the numbers that my calculator gave me. Just double checking. I have 120968. Yeah, that's what my calculator gave me. Alrighty, let's see. What are we doing? I forgot. How old was the linen wrapping? Okay. Now listen. This linen wrapping used to be 100% of what it used to be, right? It was a whole thing. It was 100% there. But then in however many years, I don't know, they didn't say it, but it took some long time. And then it lost 22.3% of its carbon-14. Now, watch very carefully. We need to pay attention to this part. They're not saying it's 22.3% is remaining. They're saying it lost 22.3%. So what I'm going to do is this. How much is remaining? Oh, this is fun. So it used to be 100%, right? But it lost 22.3%. So how much is left, really? Because that's what I need. 100 minus 22.3 is 77.7. 77.7% is remaining, okay? That is the ending amount. So I'm going to go ahead and write down what's this substance called? Carbon. So I'll say carbon is equal to the initial amount times e raised to the exponential decay rate of negative 0.000120968 times however many years t. Alrighty, let's go ahead and plug in everything we know. I'm going to say 77.7% is the ending amount, but we started with 100%, right? Times e raised to the negative 0.0. Now, if you want to, because you may be like, what happened to the unit? All right, I will put the unit there. 77.7% of, we never know how much is there originally, because they just gave us, it lost that much. But I can go ahead and stick the percent symbol, if that pleases us a little better. And then, oh dear, negative 0.000120968 t. Guess what I'm going to do to both sides now? We'll divide by 100%. What happened to the percent symbol? It cancels out, right? So that's good. So percent symbol is gone. So let me go ahead and type in 77.7 divided by 100. It says 0.777. Okay, better be accurate, my calculator. 0.777. I feel lucky, guys. Equals e to the negative 0.000. I am so sick of writing this decimal down. But we want to be accurate for this archaeologist, aren't we? Alrighty, let's solve this. Take natural log of both sides. Natural log of 0.777 is equal to natural log of e to the that. We should know by now that this will just turn into 0.0012096 t. What happened to e? Natural log of e got canceled out because that's just 1. Alrighty, let's solve this then. I swear I need more rooms, really. I'm just going to invade into this problem. Alright, so t is equal to natural log of 0.7 divided by negative 0.00012096 968. Alrighty. How old is this linen wrapping? We're about to find out. And is that important information? Yeah, it is. If it's a dinosaur fossil, we want to know how old this dinosaur was, or, you know, when did it roam the earth? All right, I divided it, guys, and I got this. 2085.79, so I'll just round it up to 8. Wow, look at this linen wrapping found at from one of the Dead Sea Scrolls. It is 2085.8 years old. So that is how we can find the answers. Years old. This was fascinating, guys. I love this stuff. Okay, let's do the last one. It says try the amount of carbon-14. Another carbon-14 problem, huh? In animal bones, T years after the animal's death is given by that equation. So they gave us the equation. Oh my goodness. Guys, look at this equation. This looks a lot familiar to, hello, what we found by scratch. It wasn't too difficult. It was just the rate that we found. But isn't it almost the same thing? Mine is even more accurate. But anyways, okay, so lucky us, they gave us the equation. Now, what are we doing with this? How old is an ivory tusk, probably from a mammoth, has lost 14% of its carbon-14. Now, it lost 14% of its carbon-14, so I'm going to say remaining. How do I spell remain? Okay, it's a tough day for me, guys. I'm gonna do 100% minus 14%. 86% is left. So 80%, 86% is remaining. So we're gonna go ahead and use the equation. P of t equals P naught times e to the negative 0.0001209 t. And plug in everything we know. We know the remaining amount is 86%. How much did we have in the originally? Of course, we had 100% of it. And then write down everything else that we know. And we're looking for t, huh? That's the only unknown variable. Did they ask for t? Oh, yes, they did. They said, how old is it? So, how many years is it? All right, divide both sides by 100. We will do 0.86 equals, now I'm saying, okay, when I was dividing 0.77.7, I was like, 0.77, yeah, of course, because we're dividing by 100. All right, that equals e to the negative 0.0001209 t. Take natural log of both sides. We get the right side simplifies and become just that long decimal times t. That means t, how old is this ivory tusk? It is as old as natural log of 0.86 divided by negative of that decimal. All right, let's figure it out. Because archaeologists probably want their decimal answer rounded. Natural log of 0.86 divided by negative 0.0001209. And that comes out to be 1246.78. So this ivory tusk is almost, it's over 1200 years old. So that's how mathematics can help archaeologists, how all these random stuff they dig up using half-life formula and natural log, because the exponential decay function. How awesome, guys. All right, that was the first 2 pages. Let's keep going. I think I have a good feeling I should be able to finish this. Okay, guys, I included page 4 because I saw a homework problem on my math lab similar to it. As you know, all Math 261 classes and at Nova, we copy, or at least at Woodbridge campus, we copy the same course template. So, I saw this, but I don't think it's a fun little problem. So, okay, I'll come back to this. All right, let's go back to page 3. business application this time, so this will be interesting to some of you business majors. Example 5, following the birth of their daughter, Michael and Sue. Yeah, wants to make an investment, Peanut, that will grow to be $10,000. $10,000 by my Luna's 18th birthday. But if I'm thinking about it, what can she do with $10,000 18 years later? Probably the money is not going to worth that much. So she may be able to use that as a little down payment for a fiat. But guys, I'm really starting this Saturday. I'm saving for my little baby girl. All right. Interest that is compounded continuously. Compounded continuously. It's like a chain reaction. Whenever I read this, guys, I write that equation down. That is the compounding continuous formula at an annual rate of 4%. R is 0.04. What should the initial investment be? Oh, guys, look, this is a kind of backward thinking. Like, we have a goal. We want the future value of our investment to be $10,000. We know the rate, BB&T or whoever is offering us 0.04%. Our question is, how much money should we put in today and wait how many years? 18 years, because we were waiting for her 18th birthday. 18 years, so that the investment becomes $10,000. So the question is, how much money should I put in the bank today? Should I put in $500, $600? You know it needs to be smaller than 10,000 because we want our money to grow in the next 18 years. So what we know is that A, the ending balance, I want it to be $10,000. What we don't know is that P naught. We don't know our initial investment. So let's go ahead and find that present value, okay? So A is 10,000. Okay, P is unknown, P naught, we don't know what that is. And we're going to multiply that by E raised to the rate. Bank is offering us 0.04. And time, we are going to wait 18 years. All right. Now look, what are we solving for? We're solving for P naught. Okay, now watch very carefully. This P naught is getting multiplied by this expression. Okay, how do you cancel out multiplication? You just have to divide. So super easy. Divide both sides by e to the 0.04 times 18th power. 0.04 times 18th power. And that's what P naught is. This is how much I need to invest today. 10,000 divided by e to the 0.04 times 18. Let me grab my calculator because I want to know how much money I should invest today. Okay, 10,000 divided by e raised to the 0.04 times 18. Oh, wow, it's not that bad. If I only have $4,867.52 today, I can run to the bank, find a place that will offer me 4% compounding continuous interest rate, and then I can just wait 18 years, and when my princess becomes 18 years old, I will give her $10,000. But this problem was kind of solving backward, right? As long as we know how to write the equation, solving part wasn't too difficult because we were able to just cancel out by dividing, right? All right, anyways, so here we have it. Well, this is super nice. They gave us a formula. The formula that I used was this P naught equals the original, the ending balance divided by e to the k times t power. This is what I used. Okay, that's what I did, right? But how did they wrote it? They said the initial balance is the ending balance times e to the negative kt power. But they're saying the same thing, isn't it? Because of that negative exponent, we can just send that k e to the kt power to the bottom. So they are the same thing. So whatever you want to use, they're the same. Okay, so let's use this formula on example 6 and 7. Okay, example 6, find the present value, find P naught of $76,000 payable at the end of 10 years. So I'm going to do 76,000 divided by e to the, what is the interest rate? 5%, 0.05. So e to the 0.05 times 10. So this is what I did above there. You see how they're very, very, very similar? But the formula that they gave us in Theorem 11 is telling us to do 76,000 times e to the negative 0.05 times 10. And as you know, they are saying the same thing, right? All right, let's go ahead and type this in. How much money do we need to put in today? 76,000 times, I'm going to do my equation, divided by e to the 0.05 times 10. We need $46.96.33. I'll say that's the same thing. That is the same thing. So it's amazing how our money grows, right? Only in 10-year period. If I just have that lump sum of money, I will wait for it to just grow on its own. I wish. All right, let's do the last one. Substance A decomposes. Now we're back to exponential decay function. I mean, briefly, we were looking at these, these business examples, guys, were actually growth functions because it was about starting from a smaller amount of money and making it big through investment. So I don't know, example 5 and 6 were kind of random, sprinkled in exponential growth function examples, but we're back to decay. A substance A decomposes at a rate proportional to the amount of A present. Okay, so this guy is called A. The substance is called A. Write an equation that gives the amount A left of an initial amount A naught after time t. Exponential decay function. So it goes like A equals, what's this? A equals A naught, the initial amount times E raised to the negative, what's the rate? Oh, they never said it. We're just going to keep it as negative K times T. So this is just a general equation with nothing plugged in. What do they want with this? We'll use this in part B, I guess. All right, so here's my answer for part A. Part B. It is found that 16% of A, they could have been a little more creative with this substance instead of just calling it A. But found that 16 pound of A will reduce to 8 pound. Okay, so ending amount is 16 pound. But beginning amount, no, I got it backward. So we had 16 pound in the beginning, right? But then it reduced to 8 pound, it decomposed. So initial amount is 16 pounds. Sorry about confusing you earlier. But ending amount is 8 pound. And how long did it take? It took them 4.2 hours. What is it? What is this substance? I'm looking at the number 16 and 8. Half of 16 is 8. They gave us a half-life just now. All right, now let's ask the question. What do you want? After how long will there be only 1 pound left? I don't think I need mathematics to... okay, I think we can just use this half-life idea. How about we try that, guys? Let's see. So we have 16 pound in the beginning, right? 1 half-life. 4.2 hours later, we got 8 pound, right? Take another half-life. Another 4.2 hours later, we're down to what pounds? 4 pound. Take another 4.2 hours, which is the half-life. Guess what? Now we're down to 2 pounds. Take the last half-life. It's going to be 1 pound left. And we can go on. It's going to be 0.5, 0.25, blah, blah, blah. But how many half-life does it take for this substance to become 1 pound if it started from 16 pound? I am having 1, 2, 3, 4 half-lives. So I can do 4.2 times 4, which is 16.8 hours. So we were able to just solve this using the idea of half-life. But how would I do this using that equation? Let me try that up here. So what we got is 16 equals, I apologize, that's not right. A is 8 equals to 16 times e raised to the negative k times t of 4.2. Okay? If I solve this, I get divide both sides by 16, which is 1/2 equals e to the negative 4.2k. Take natural log of both sides, negative 4.2. Okay, you see how this method is a little more complicated? But what I want to see is I want to get the same answer, 16.8 hours. But let's continue then. I got to find the exponential decay rate. All right, then k is equal to natural log of half divided by negative 4.2. Okay, natural log of 1/2 divided by negative 4.2 is equal to 0.165. So using this, I'm going to write my equation. A equals, how much did we start with? A naught is 16 times e to the negative 0.165 t. Alrighty, I'm going to go ahead and use this equation and find out what t do we need to make the ending amount to be 1. Okay, so let me bring this down. This is super fun. 1 equals 16 times e to the negative 0.165 t. Divide both sides by 16. So this is the mathy way of solving this equation. But we already know the answer should be this, right? Let's continue though. 1/16 is equal to e to the negative 0.165 t. Take natural log of both sides. We get this. So t will be natural log of 1/16 divided by negative 0.165. I am so excited. I want to see 16.8 when I type this into my calculator. Divided by negative 0.165. What did you guys get? Look at that. 16.8 hours. So this is up to you. You know which method I prefer. I like this method. This one was short and quick. We just had to understand, or we just had to notice that they secretly gave us the half-life because they went from 16 pound to 8 pound in 4.2 hours. So if I were to do this, if I see this problem on your homework, I would stick with this method because that was much easier. But it doesn't mean that we don't know how to solve for k, that exponential decay rate. We know how to write that equation, and we can use that equation to solve for that unknown t value by plugging in 1 into a. So so many different ways to do a single math problem, right? I love it. You know, technically this is it for section 2.5. Because the last section right here is just talking about shapes of the function. Now you guys know a linear function. Like if I ask you, hey, what does y equals mx plus b look like? Then you know, oh, that is a straight line function. It's just going to be a straight line function. So what I'm giving you over here is a couple different types of functions. If you have dots are in this quadratic or a parabolic shape, and if you can imagine fitting a parabola, this one is opening downward, and then if the dots resemble that quadratic or the parabolic shape, then we know the equation that we can use to fit that curve will be y equals a times x squared plus bx plus c. So this is just a quadratic. Basically, we look at the shape of these dots, try to draw a regression curve, and then, that's a parabola, so we know it must be quadratic. What about this one? It's not a parabola because to be a parabola, it needs to go down that way. But it comes back up, so it's a nice curve looking like that. And to me, that looks like a cubic function. So it can be cubic, but something like this, like a W shape, that could be a quartic function. But I know in Math 161, you learned this basic shapes of function by looking at the end behaviors and the degrees of the function. So, but it can be cubic, it can be quartic, it can be fifth degree, sixth degree, any polynomial function with these nice curves, okay? And this is just a general way of writing any polynomial function by plugging in n to be like 3 or 4 or, any. There's really nothing to teach about here other than just, guys, you should look at the shapes of these dots and try to connect the dots. Now, what about this one, though? I like this one. So this is the one that we were doing in this section. Look at the growth. Definitely not linear, right? This is going up. The slope, the rate of change was kind of smaller here, but all of a sudden it's going up rapidly, like that painting value problem or like that investment problem. I mean, if you invest more money, you get more interest. Okay, and that is how people with lots of money make more money compared to someone who only has $500 in their savings. We're not gaining much interest on that. But this is a shape of an exponential growth function, and this is an exponential decay. This is going down. Okay, it's going down. Okay, you keep on taking half and half and half and half and half of something. Could be a different rate. But just wanted to show you a couple of the shapes. Now, we also, I guess we can look at logarithmic function, but have you guys graphed logarithmic functions in Math 161? I hope you did. See, logarithmic functions will have a vertical asymptote, but I don't know in 261 if we will ever get to the graph. Maybe we'll see, but not in this section because we're focusing on the application problem, finding the derivatives instead of graphing part. And the very last one, this one is very interesting, logistic function. This is something that I used in my graduate study to do a regression, a logistic regression. This is fun one. Now, I don't know if you have an example, but maybe you have seen an example of fish population. You see how in a pond, let's say a Potomac River or somewhere like in the water, and you have these fish, like fish number 1, fish number 2, fish number 3. Say that fishes are reproducing, okay? They're growing, their population is getting big, okay? So maybe you start with 2 fish, and you 4 fish, and then what's next? Like 8 fish, 16 fish. So say that they are doubling like crazy, okay? 2, 4, 8, 16, like 32, 64. Well, if you continue with this, 64 times 2, 128. Now, let me just continue real quick. Times 2, 256. Times 2, there was a game that I used to play. Every time I move these tile pieces, they became double. But if you keep on doubling, it's going to grow like crazy, okay? 2048. But in couple steps, you're going to hit a very big number. But is that realistic in a fish population? Can I have 3 billion fish in Potomac River? Not really, right? So, oh my goodness, I only have 5% on my iPad. So, what we can talk about is this fun logistic function. Oh, I wish I had an example where it kind of sets us a limit, okay? The growth will not continue forever, guys. There is a realistic limit that we're not going to be able to cross. So if the fish population, they're going to keep on growing, lots of fish. But we're going to have a maximum. And logistic function somewhat grows like an exponential function in the beginning, but it kind of levels out. And it's not going to go over that maximum limit, okay? If you like this stuff, you want to talk about more examples, I can find more examples, and we can go over them next class. But if it is on a shape of this, what shape would you say? S shape? It's like an S shape, isn't it? Like, ooh. If it's in that shape, then logistic regression will be the best to model the scatter plots or the data points. Okay, so just kind of wanted to show you a whole bunch of scatter plots, some dots, and different models that are best fitting for these nonlinear regressions. It's kind of random. What are we talking about this right now? But if you see homework problems on it, here you go. Here are your notes on it. if you want us to do some application problems involving logistics function, we should be able to do that. I think I saw some fun examples, but I think what we went over is enough. We did 3 sections today on November 11th. Thank you guys for doing this asynchronously today. I would rather teach it. Look at the time. It's already 2 o'clock. It's taking longer for me to teach asynchronously too. But anyways, I'm going to go ahead and stop the lesson. I hope you guys have a great rest of the week. I'm going to get busy grading your exam 1 this weekend. So you'll see your exam grades popping up. But go ahead and definitely do these daily problems for me now. Daily problem 2.4 and 2.5. You will find it over here. It's word problem. Why am I giving this to you? Because you will see a similar page on your exam too. I'm going to try to come up with more application problems to put on the exams because I don't want these photo math or math ways to just give you all the answers and works because that's boring. I want you to be able to actually do them. So I'm going to probably put some fun word problems on the exam. So I want you to be ready for them. So here's a practice problem that I want you to try. If you're doing this dosage problem and this decay rate, doubling time problem, you're like, I don't know how to do them. Write me an email. I will go over them and I will share you with the video link, okay? But that's it for this week. Hopefully my babysitter comes back to work next week so that I get to teach